This is a short little lecture video about current running through the human body and the ways damage can occur when current runs through the body. The most important factor in all of this, as you're going to see, is the resistance that the human body provides. You can think of the body as like a resistor. Resistance going through two spots of the body depends pretty strongly on whether the skin is dry. You know, it can go all the way from perfectly dry to really saturated with water. And if the skin is dry, the resistance is somewhere between about 2,000 to 10,000 ohms. And we're going to see in these calculations a lot that these ranges are pretty unsatisfyingly big, which means, you know, we'll look at the effect of being at the different ends of these ranges, but you know, in a lot of cases, you just don't know enough to know how dangerous a certain amount of electricity is going to be because you don't know exactly what your resistance is. You know, there's all sorts of things that can happen to affect this resistance. Your skin has different thicknesses. Different people's skin has different thicknesses. If you're touching something with electricity running through it with a hand that has calluses on it, you know, that can affect it. And that's the kind of stuff that affects these ranges. If your skin is wet, this goes down a lot to, we'll call this range 500 to 2,000 ohms. And one thing that's interesting about this is, like, doesn't it matter whether current is going through 1 inch of your skin or a centimeter of your skin or a meter from hand to hand? Doesn't that make a big difference? It turns out that doesn't make a huge difference because the much bigger part of resistance that your body provides to electrical current is at the skin. The skin provides the biggest chunk of that resistance. So like we'll see later when we're talking about pacemakers that we're talking about much lower resistance because it doesn't have to go through the skin. It's embedded in your body. Okay, so the effect that electricity has going through your body depends on the electric current. And so here's the list that we're going to use of, you know, what different amounts of current going through your body can do. I'm going to do all of these in milliamps. So remember that 1 milliamp is equal to 1 times 10 to the minus third amps. Okay, so the first threshold is at about 1 milliamp. You start to be able to notice the shock or whatever. You can feel, it's not necessarily pain, it's not pain, but you can feel that little bit of buzzing that that demonstrates, you know, that you can notice that current. 5 milliamps, somewhere around there, is the maximum harmless current. And now we're going to start getting into things that that can cause damage to tissue. Between about 10 to 20 milliamps is where you can get sustained muscle contraction. And so this can be a dangerous point because if that muscle contraction is in your hands and your hands are holding on to the thing providing the current, like a wire, this can make it so that you can't let go. And so that current just keeps flowing and flowing. At 50 milliamps, that feeling of a shock starts to become painful. Somewhere in the range of 100 to 300 milliamps, if this current is going through your heart, you can get ventricular fibrillation. So this is the first level where we start to be concerned about, you can die from this. But of course, that current has to go through your chest, and we'll talk about, the fact that current, you're mostly going to assume that current is going to take almost entirely the shortest, least resistance path through your body. So we'll talk about that. At about 300 milliamps, we start to have danger of burns. And then at 6,000 milliamps, and so that's 6 amps, so we're really bumping it way up here. This is where you can have really sustained ventricular fibrillation. And paralysis of your breathing. Okay, so the first thing that I want to talk about is all of this is in terms of current. Okay, so current and voltage are different things. So does the voltage matter for this? And so for that, I want to demonstrate how, yes, voltage is really important for all of this, because voltage is the thing that puts the current through your body. So for the first example, and keeping in mind that the dangerous thing is the current going through your body, let's say that a person is holding on to a wire that electricity is flowing through. Okay. And let's say that the current flowing through this wire is 10 amps. Okay, 10 amps is a ton of current. It's much higher than anything on this list. And so if that 10 amps is flowing through your body, especially from hand to hand, you're in big trouble, because a current goes from one hand through the other hand, is going through your shoulders, straight through your chest. And so your heart and your lungs are going to get a lot of this current. Okay. And so the question here is, how dangerous is this situation? And I'm going to do this in two cases. First, I'm going to say that the resistance in the wire is 0. And then second, we're going to give it a little bit of resistance. All wires have a little bit of resistance. This actually is quite a big amount of resistance for, I mean, the way I've drawn that wire, this big, huge wire, you would never have a full 1 ohm resistance in a wire like this. But let's say, as kind of the other extreme, we'll say that the resistance in the wire for this portion of the wire so this is the wire just between the hands. Is 1 ohm. Okay. And we're going to calculate the current flowing from one hand to the other hand through the body in both of these two cases. Okay, well, I want you to notice that what we have here is sort of like a circuit. I mean, it is a circuit. You'll have some kind of voltage that's creating this current. And somewhere there has to be a resistance, or else this current would be flowing infinitely fast through this wire. I'm going to put the resistor over here. I'll just call it, well, I'll call it R. You know, we don't know what that resistance is. Another place I could have put it is as internal resistance in the battery, but I'm putting it over here. And then the person's hands and the person's body we're going to treat as another part of this circuit. And I'm going to write this as, for now, I'm just going to say this is the resistance of the body. Okay. And what we know is that the current flowing through this wire is 10 amps. Okay, that's what we're given in the problem. And we want to calculate the current in going through the body. Well, I'm going to circle one node, and this is going to tell us the situation. So this part that's circled in red is all one node. And the one thing that you know, the most important thing that you know about a node is that the electric potential is the same everywhere on a node. So the electric potential is the same, that's a crazy M, at every point on a node. And so what that says is, remember the voltage going across this resistance of the body is the difference in electric potential between the two sides. And so since both sides of this resistor are on the same node, the voltage across the body is 0. Okay? And now if you think of Ohm's law, there's a relationship between the resistance and the current and the voltage that says, you know, the voltage, 0, is equal to the resistance times the current. Okay, so that's what we're trying to find, is this current going through the body. And this equation tells us that the resistance the current going through the body is 0, okay? And notice that that's true no matter what the voltage is of the battery, the resistance in the circuit, the resistance of the body even, whether it's soaking wet or you got lucky and at this point the resistance in your body between those 2 points is 10,000 ohms. No matter what, you have 0 current flowing through your body. So you're touching with both hands this very high current wire, but none of that electricity is going through the body. Okay, so there's no danger in this case. Okay, but all wires do have some resistance, so we have to consider that. And so basically I'm trying to kind of bracket this question where we've considered the wire with 0 resistance. Now we're going to consider it with an kind of impossibly high amount of resistance and see if current goes through the body. Okay, so first I'm going to do it with, let's say the body's resistance is as big as it can be, 10,000 ohms. And then we'll go back and do it with kind of the resistance as small as it can be, 500 ohms. And, we'll see what we can figure out about this range of possibilities. Okay, so this time the resistance between the two hands is 1 ohm. And the resistance in the body we're going to assume is 10,000 ohms. You're always better off if your body is providing more resistance. So in every case, your best hope is that your body is providing 10,000 ohms of resistance. Since this is 1 ohm, in order to produce a current of 10 amps, we only need a voltage of 10 volts, okay? So that makes this, the current is going this way through that resistor at 10 amps. Maybe I should, as I think about it, maybe I should just do this. So we'll set this up like a circuits problem, get a little practice with circuits as we do this. Okay, this current, well, we know it's 10 amps because that's what's given in the problem. The voltage has to be, the drop has to be in the direction of the current. And Ohm's law says that the voltage is going to be the resistance times the current. So this voltage is 10 volts. And then we have a voltage across the body. And really what we're trying to find ultimately is the current going through the body. Okay, so let's solve this current. Let's solve this circuit. There are 2 nodes, and they both say the same thing. So we're only going to use Kirchhoff's current law in one of these. The other one is on the other half, and if you do it, you'll get the exact same equation. So this equation, Kirchhoff's current law, says we have a current going this way. I battery is going into the node. 10 amps and I body, I battery. Let's call it like that so to keep these two separate. But leaving the node is 10 amps and the current leaving the body. Okay, so Kirchhoff's current law says the current from the battery is equal to 10 plus I body. We have two variables left, and so we're going to need to use Kirchhoff's voltage law twice to get a system we can solve. So Kirchhoff's voltage law, let's first do the lower loop, and I'm going to go clockwise around this lower small loop. So we have a voltage rise of 10 for the battery if I'm going clockwise. And now we have a voltage drop of, well, also 10. Okay, that didn't help. We already knew all that stuff. So now let's go to the top loop. And that says that if I go clockwise, so I'll start over here to the right of this 1 ohm resistor, we have a voltage rise of 10. And then we have a voltage drop of VB. And this voltage VB, because of Ohm's law, is equal to 10,000 times the current through the body. And so now, since all we care about is the current going through the body, this is all the equation we need. We need another one to solve for the current coming from the battery, but this is fine. So we have 10 is equal to 10,000 IB, and so IB is 0.001 amps, or 1 milliamp. Okay, so with this gigantic current and kind of the most dangerous case of this resistor, of the resistance in the wire, we're saying that it's 1 ohm, which is probably higher than it is. You get just over the threshold where you can feel electricity in your body. There's no danger in any way. But this is in the case where you're lucky and the resistance between your two hands is 10,000 ohms. So what if you're soaking wet, the skin on your hands isn't that thick, whatever. Now we're going to go to the smallest possible resistance of your body and see what the situation is there. Okay, so we have whatever is pushing the current through this wire. We have our 1 ohm resistor. We know that the current here is 10 amps. That means that we know that the voltage is 1 times 10. So this is 10 volts. And now we have the body. This time we're going to assume that the resistance of the body is only 500 ohms. So that's a pretty huge difference. That's 20 times less than it was before, and we're going to see that effect. And we want to calculate the current through the body, and it's going to be helpful to know from Ohm's law that the voltage across the body is 500, that's the resistance, times IB. And we have the voltage for the battery and a current going this way, I battery. Okay, the nodes work just the same way they did last time, so I'm first going to use Kirchhoff's current law over on this side. We have one current going into the node, that's I battery. We have two currents going out, the 10 at the 10 across that point in the wire, and then the current going through the body. And now we'll use the voltage law. All we're trying to figure out is this current IB. So again, I'm going to use the small upper loop. So if I go clockwise, starting to the right of the wire's resistor, I have a rise of 10 volts. Then I get to the top and I have a drop of 500 times I body, and that's a voltage. And now we can just directly solve I body is equal to 10 divided by 500. And this gives a current of, well, it's going to be 20 times bigger than in the case where the resistance was 20 times bigger. So this is 0.02 amps. And if you write this in milliamps, you have 20 milliamps. Okay, so where does that fall on our list of dangerous things? This can cause muscle contraction. It might make it difficult or impossible to let go of the wire. It should not be big enough to cause fibrillation in the heart, to make the heart stop beating as it's supposed to. But you can see we're well into the range of a concerning current if it's going through your lungs and heart. Now I keep bringing up this thing about how, where is this current traveling in your body, and saying that that's important. Okay, so let me give another case where you don't have your two hands on two spots on the wire. Instead, it's just like a single hand. So how your body contacts the wire is important. So let's think now about a case where so there's your hand. And the wire is going through here, okay? And let's think of a case where we have sort of a dangerous amount of current. Let's say that the voltage between these two spots, we kind of learned in the last example that that's what really matters here, is the voltage between the two spots on the body. So let's say that is, let's say that that's 120 volts. And I'll choose that because that's the voltage that comes out of the outlets on your wall. And let's say that the resistance, we'll pick somewhere kind of a lower resistance in the range of possibilities, but somewhere in between the max and the min. Let's say 2,000 ohms is the resistance that your body provides. Okay, so we're going to model this as this resistor is the hand. Okay, the wire isn't in this picture. The wire is just providing this voltage. And so we have a voltage here of 120 volts. And then we have a current here. That's the current going through the body. And we'll use Ohm's law to figure this out. So Ohm's law says 120 volts is equal to 2,000 times the current going through the body. You can just immediately solve for the current going through the body, and you get 0.06 amps, or 60 milliamps. 60. Okay, this can be a dangerous current. There's no question about that. But the path that this current is going to take is just going to tend to be, let me use a different color. It's just going to tend to be through the hand like that. And it'll take a few different paths, okay, in different amounts. But essentially, none of these current paths are going to get all the way up your arm to your chest. Your chest is going to have zero current flowing through it. And so even though this is moving up the list of dangerous currents going through your body, the fact that it's just going through your hand means, yeah, you might have muscle contraction. You'll feel some pain. Is that what I said? Yeah, it's a little over the pain threshold. But your life is in absolutely zero danger. If, on the other hand, where your thumb was one of your hands, and where your pinky was another one of your hands, and you had all these same values, that 60 milliamp current could pose a danger. Okay, I want to do one more example problem. And this one deals with a pacemaker. So let's say that a pacemaker and this is embedded in your body, and it creates a voltage across your heart. Well, not across your whole heart, it's just across the part of your heart that you use for timing your heartbeats. So I'll say it creates a voltage across, the heart cells, the important cells for creating a heartbeat. Of 6 volts. We're going to assume that the resistance of the heart cells is 500 ohms. So first, let's calculate the power that's delivered by the pacemaker battery to these heart cells. And then second, we're going to do a calculation that would be important for figuring out the battery life. So we'll say that this voltage is created for half a millisecond. So it's a very short burst of voltage, 70 times a minute, because that's how many heartbeats we want. And we want to know what's the total energy delivered to the heart cells in a year? Okay, so for part A, we're going to think of the heart cells as a resistor. And it has a resistance of 500 ohms. That was given. And we have a voltage of 6 volts. And we want to calculate the power in that resistor. I'll call this I heart. Okay, so do you remember the calculation for power delivered to a resistor? The power, remember, is equal to the voltage across the resistor times the current through the resistor. And that means we need to calculate that current. And so we can use Ohm's law. Ohm's law always gives you the relationship between the voltage and the resistance and the current for a resistor. And so we have that 6 volts is equal to 500 times the current through the heart cells. And you get a current going through the heart cells of 0.012 amps. Or 12 milliamps. So now that we have the voltage and we have the power, we have the voltage and we have the current, we can calculate the power. Hold on a sec, little computer glitch. And the power is equal to 6 times 0.012, and that is 0.072 watts. Okay, so while this voltage is present across the heart cells, the battery has to be providing a power to those cells of 0.072 watts. Okay, so now we're going to get into using this power to calculate some things about total energy expenditure. Okay, so this is the power while the pulse is happening. So now let's figure out the power or the energy in each one of these pulses. Well, the total energy is going to be the power times the time that this power is being provided to the resistor. So we have the power of 0.072 times the time duration for a single pulse. Half a millisecond is 0.0005 seconds. And we get 3.6 times 10 to the minus 5 joules. We've had everything in SI units, so the answer for energy is going to be in SI units too. Okay, so that's each pulse. Well, now we can think about the energy in a full minute. There are 70 of these pulses every minute. So the total energy in a minute is just 70 times 3.6 times 10 to the minus 5. And you get a total energy for a minute of 0.0005 0.252 joules. We want it for a year, so now we just have to multiply this by the number of minutes in a year. And so we'll take 0.00252. If we multiply that by 60, that gives us the energy in an hour. If we multiply that by 24, that gives us the energy in a day. And if we multiply that by 365.25, that gives us the energy in a year. And if you multiply this all out, you get 1,325.42 joules. And as you can imagine, this calculation is really important if you're trying to figure out how long this pacemaker battery is going to last before it has to be replaced. Now, without doing any calculations, I just want to talk about one more thing really quickly, and that is grounding. You know that wall outlets usually have a third, a ground prong. Old outlets used to just really have 2 prongs, no grounding prong. And so what does grounding do for you? And so I guess let me draw a little sketch here, and I'll try to convey what's going on. So let's say that this person is holding an electric drill. He loves using that drill. Okay, so what happens with the electricity is you have a current flowing through a circuit like this, and the electricity coming from your wall is always alternating polarity, but we're going to pretend that it works like a battery just for simplicity. And so we'll say that this is the positive, and then this is the ground. That's the symbol for the ground. Okay. Well, what happens if, so everything is fine as long as this electricity stays in the current. Stays in the wire, I'm sorry. But what happens if some break happens in this wire, or something occurs that lets this positive line connect to the case of the tool that you're holding? Okay, so let me move down here. I'll copy this. Whoop. Okay, stay with me. Okay, so I'll copy this, paste it down here. So now this time I'm going to draw the positive coming from the wall. But this time the wire's broken, and this positive goes to the case of the tool. Well, now you are unfortunately part of this circuit, and this circuit goes through the case, through your body, and connects to the ground that way. And at that point, your expression changes, you know. So this is you. That's when a shock occurs. So what the grounding does is there is another wire that goes from the case of the tool. Guess I'll keep making that red, to the ground. Okay, so if the electricity comes in, this positive comes in and goes to the case. Instead of going from the case through your arm, through your body, and back to the ground, now this grounding wire that's connected to the case of the tool provides an easier path for the electricity to follow to get to the ground, and that electricity will take that grounding wire rather than taking the path through your body. So that's the importance of grounding tools that are operating at very high voltages.